Ready? How about we start now? Okay, thanks everybody for joining, and thanks our speaker. So actually, I encourage for those of you who joined the talk to open your camera, so our speaker can also see your face during her talk. Okay, so now I'm delighted to introduce our speaker today, Professor Chelsea Feng from Stanford University and Google Brain. As many of you already know, Chelsea is a leading figure in robotics learning, and her work has been widely acknowledged by many mediums and by many influential awards, such as CCM Doctoral Dissertation Award and MIT Technical Review Certified Pioneering Reward. So there are definitely lots of achievement and contribution Chelsea has made so far, but I won't waste time on going through all of them. But I hope you can all join me in welcoming Professor Feng to the RI seminar. Welcome.
Thank you so much, Wenzen, for the introduction. Before I start, I'm very happy to be here virtually. There's a lot of really amazing work in robotics and machine learning that happens at CMU, and it's been a pleasure meeting some of you this morning. Also, if you have any questions in the middle of my talk, feel free to raise your hand. I can monitor the list of participants. You're also welcome to answer questions in chat, although I won't look at those until after the talk, but I'm also happy to answer questions at the end as well. So with that, let's get started. So I'd like to start actually with a bit of a story that maybe some of you might be familiar with. And in particular, the story starts at the beginning of my PhD. I was working on how we might enable robots to learn manipulation skills, like putting this red block into a shape sorting cube. And in particular, the robot is learning through trial and error, or reinforcement learning, and it's trying to learn a policy that maps from images taken from the robot's camera directly to torques applied to the robot's joints. And at the beginning of the learning process, the robot was moving around randomly, and through trial and error is able to figure out eventually a policy that consistently places the red block into the shape sorting cube. And we were pretty excited about this result. And here's the final policy that you can see, where you can see the viewpoint from the robot in the bottom right. And we were really excited about this result, not because the robot had learned how to play with this children's toy, but because there was basically this seemingly general purpose algorithm that could enable a robot to do a variety of different skills, including placing the claw of a toy hammer underneath the nail and screwing a cap onto a bottle. And in kind of some follow-up to this work, we were also able to train a robot to use a spatula to lift an object into a bowl. And this last task is quite challenging because the robot needs to fairly aggressively maneuver the spatula underneath the object to be successful. So we were really excited about these results. It seemed like we had something that could allow robots to learn a variety of different skills in the real world. And at the same time, other people took these kind of ideas and applied them, kind of advanced them and applied them to their own robots to enable a PR2 to hit a puck into a goal, to enable this robot to open a door, and to allow this PR2 to throw an object to hit a certain target. And around the same time, there was also a lot of work on deep reinforcement learning for playing Atari games, for playing Go, and for robotic locomotion and simulation. So this is all really exciting. It seemed like maybe this was kind of a significant step towards allowing robots to be useful in the real world. But with that said, we had a really big problem. And the problem is that the robot didn't learn how to use spatulas to lift objects or how to open different kinds of doors. The robot learned how to use that spatula to lift that object into that bowl. And if you gave it a different spatula or a different bowl or a different tablecloth even, the robot wouldn't be able to succeed. And that's because the robot is learning one task in one environment, starting from scratch, tabula rasa. And its whole world is that one tablecloth and that one spatula. Now, you might say, okay, well, we can solve this problem. We just need to give the robot more spatulas, and then it will be able to generalize to different kinds of spatulas. And while this would work, it seems like this is perhaps missing the point. In essence, what this sort of reinforcement learning approach, it seems very reasonable for training robots, but it's kind of analogous to giving a baby on day one a spatula and trying to train that infant to use spatulas to lift objects, which seems kind of ridiculous when you look at it from that standpoint. And so it seems like we need to rethink the way that we're approaching the problem if we ultimately care about having robots operating in real environments and generalizing to all sorts of objects in all sorts of settings. So one way to think about this problem is from the machine learning standpoint. Essentially, we have this mismatch between the data distribution that we're training the robot on and the desired test distribution. For example, we're training the robot in the lab environment, and we want our robot to be able to generalize to the real world. And now from this standpoint, it seems like we need to, machine learning isn't going to work in this setting, and we need to kind of think about something else. Now, one natural reaction to this problem is, can I build my knowledge into the algorithm? I know how to use spatulas. I know how to solve all sorts of problems. Can I try to build my knowledge into the robot to help the robot be able to generalize to different situations? For example, I know things about physics. I know things about objects and how the robot should be equivariant to transformations of the object, for example, and maybe I know something about different architectures. However, while this reaction is very natural, I think that it's flawed in a couple different ways. First, while we humans are really good at generalizing to different environments, we don't know exactly how we do it. And second, even if we did know exactly how the human brain worked, we also don't know how to translate that into AI systems. And so it seems like we should be able to do better than this. And it seems like we should be able to develop robots that can generalize without building knowledge into the system. One thing that we can learn from humans, perhaps, is that humans accumulate and learn from broad data and broad experiences. Instead of training a robot on like a few hours of data in one room, can we allow robots to interact with lots of different objects in lots of different environments? Essentially, if we want robots to generalize broadly, maybe we should think about training them with equally broad data. We could essentially try to solve this problem by widening the training distribution on which we train robots. And the corollary to this is that it's not just about acquiring broad data, but also developing algorithms that can learn from scalable data sources. And this isn't something that's really straightforward or easy. The algorithms that I mentioned before can't be directly applied to large unlabeled data sets, for example. And I really emphasize scalable here because it's not necessarily about like self-supervised data sets or kind of being able to translate to like be able to learn efficiently. It's really about being able to scale to things that we can collect easily, whether it be labeled or unlabeled or whatever it may be. Okay, so towards this question, there's two things I'll be talking about in my talk. First, how can robots acquire broad and diverse experiences? How can we get that data? And second, how can algorithms learn from such data? So essentially, I'll talk about the data and the algorithms. Okay, so let's first start by talking about how we might acquire data. And to do this, we can maybe first look at what does our data look like in robot learning. So about 3 to 4 years ago, or maybe closer to 5 years ago at this point, the data looked like a single object, a single task, and a single environment. Fortunately, more recently, we've made more progress. And for example, 2 to 3 years ago, we've seen works, including work done at CMU with many different objects, but still really trying to solve a single task like grasping in a single environment. And then more recently, we've also seen works that are actually looking at many objects and many different tasks, but still in a single environment. So we're clearly making progress in terms of collecting more diverse data. But if we translate this data, if we kind of compare this data to data in machine learning, things don't really kind of compare. If you look at something like ImageNet, which was of course done 10 plus years ago, it's really kind of substantially more diverse than the things that we're looking at in robot learning, with many objects, many tasks, many environments, viewpoints, lighting, and so forth. And as a result of these large data sets, we see broad generalization. So from the machine learning point of view, it seems like the data that we're training on in robotics is much narrower than data like ImageNet. It has much more limited diversity with a single viewpoint, a single environment, and so forth. So this is the machine learning point of view. It seems kind of clear from the machine learning standpoint that we should diversify. However, from the robotics standpoint and the robotics point of view, we don't want to have to collect all of ImageNet on a robot. And the current paradigm for robot learning, and especially robot reinforcement learning, is to set up an experiment, collect data, run learning on that data, and then when we set up a new experiment, we throw away all the data, rinse and repeat. And if we hope to acquire generalization at the level of ImageNet, then maybe this paradigm isn't quite the right solution. Because if we wanted to collect something as broad and diverse as ImageNet, for example, we would need to do that for every single experiment that we ran. And it's obviously not practical to collect ImageNet for each experiment. So maybe something that we could do instead is to accumulate and reuse data sets across labs. Now, this is also quite challenging because different labs have different robots, have different environments, different experimental setups. But I think perhaps there's some way that we can make progress on this. So if we were to collect data across labs and share data across labs, one question is, how should we go about collecting that data? We could collect data with random actions. For example, data that looks like this, where the robot is basically selecting actions from some distribution, executing them sequentially, and so forth. And we could also give it deformable objects, for example, and also program in random actions and collect data this way. The good news with the data collection scheme like this is that we can actually collect a lot of data this way. And some of these interactions are actually surprisingly interesting to some degree. And one of the things that we did to try to actually start collecting and sharing data across institutions is we collected a lot of data this way on different robot platforms across different institutions. So this is kind of the result of that effort. This was data collected on 7 different robot platforms across 4 different institutions: UC Berkeley, Stanford, Google, and University of Pennsylvania. And it's hopefully, I think, a first step towards actually trying to share data and accumulate data across institutions. There's 15 million video frames, 113 different camera viewpoints. And importantly, it's also open for contributions so that we can hope to start accumulating more data and sharing data. Of course, now what remains to be seen is we can collect all this data, but is this data actually useful? And I'll talk about this in the second part of my talk when I talk about how to actually develop algorithms that can learn from scalable data sources. Okay, so collecting random data is one way that we could approach the data collection problem. But the downside of collecting random data is that the utility of this data is going to be limited. If we're collecting completely random actions, then that exploration isn't going to scale to tasks like using a spatula, for example. So how might we go about collecting more interesting data, data that has more useful and sophisticated interactions with objects? So one kind of common approach in robotics is to collect demonstrations where we just guide the robot arm through different motions. We can collect a lot more useful and interesting data this way, including data of using tools, for example. But the downside is that we can't collect a lot of this data because it requires a significant manual effort of actually guiding the robot through those arms. You could also teleoperate the robot to do something similar. It requires a human in the loop. Another approach might be to provide videos of humans. So for example, there's awesome data sets like this one, like the Epic Kitchens data set of humans doing all sorts of really interesting things. And this is something that a mechanism that we can get lots of really, really interesting data. The downside with this data, of course, though, is that it's pretty hard for a robot to use it because the morphology of the human is different from the robot, and the appearance of the environment, and the human's arms are different. We'll come back to this a bit on how we might learn from this, but this is, I think, one promising approach in which we might be able to get lots of interesting data. But it still seems like we need to think about how we can collect useful data in a scalable way. Random data gives us very scalable data, but maybe not data that's especially useful, whereas human demonstrations gives us very useful data, but not in a scalable way. So we need to somehow have a method that gives us both of these two things. And so this is where algorithms for better robotic exploration might come in. The first approach that we thought about was approaches that try to seek out novelty. There's actually a very large body of work on these kind of curiosity-based algorithms. And we wanted to run this on a robot to see if it could allow us to collect useful data in a scalable way. And in particular, we had, in this case, we had one task. We wanted the robot to be able to open this drawer right here. And we ran the algorithm to try to collect data that included interaction with that drawer. And in particular, we ran this particular algorithm plan to explore, which is, I think, one of the state-of-the-art methods for exploration and novelty seeking, and can in principle scale to image observations. But unfortunately, when we tried to run this algorithm on a real robot, it didn't lead to very diverse interactions. It may have led to things that seemed novel from the standpoint of the camera, but didn't actually interact very much with the drawer that we cared about, or many of the other objects in the environment. So now when we're thinking about this problem, novelty-seeking approaches are trying to approach the problem completely autonomously and having the robot just explore on its own. And I think it's worth thinking about how we might have a user help the robot collect more interesting data, ideally in a way that doesn't require a human in the loop. It seems like a user should be able to help show the robot interesting things to explore at the beginning, and then allow the robot to autonomously collect a lot of data, leveraging that supervision provided at the very beginning. And kind of much like drawing upon the thread of being inspired by humans before, humans also don't go about things completely unsupervised. Humans have parents that kind of show them interesting things and so forth. So this doesn't seem completely out of the blue. And so the way that we do this is we first show examples of interesting states to the robot. So we show it a few examples of images where the robot is opening this drawer. And then we simultaneously learn a classifier to classify interesting examples versus data that the robot explored. So we can basically just train a binary classifier that classifies between the human provided states and the observations that the robot encountered when trying to explore. And then try to explore in a way that finds images that are classified as interesting. This requires only positive examples of interesting states from the human at the very beginning, which can be collected in a few minutes. And then the rest of this process is completely autonomous as it simultaneously learns this classifier and tries to explore in a way that leads to these more interesting states. And what we find is that after just around a few minutes of human guidance and running autonomous exploration, we find that the robot is able to actually explore this drawer as indicated by the example images. And it also kind of plays with the drawer in a way that kind of shows that it's exploring around these interesting states. And then further, if we quantitatively compare these two algorithms, the novelty-seeking approach disagreement or this batch exploration with examples approach, we see that we're able to significantly increase the interaction with the handle of the drawer and the drawer itself by a little bit of supervision. So the takeaway here is that a small amount of human guidance can really go a long way in terms of enabling more interesting data collection. Okay, so that's the first part. That's kind of an overview of some of the work that we've done on allowing robots to acquire broad and diverse experiences. Now that we have mechanisms to collect this kind of data, how do we actually go about learning from this data? Dave, do you have a question?
Yeah, I was just curious about the last project you just described. Like you said that the states were like interesting, but I mean, it sort of seems like just a way of giving demonstrations to the robot? Is there like a distinction that you're making?
Yeah, so one thing that's a little bit different from demonstrations is that it's examples of states, so you don't have to show the robot the entire trajectory of the behavior. In principle, you don't even necessarily need to have the robot arm in the scene, although in like a certain position, although in these experiments we did. And I think it could look a bit more like demonstrations, although we collected only like 3 minutes of this data. And if you collected demonstrations and tried to imitate 3 minutes of demonstration data, it probably wouldn't work out quite as well. But it is kind of along the lines of providing examples. And you could also kind of provide it something like demonstrations instead of providing these states, and the algorithm would still be able to proceed.
Okay, cool. Yeah, thanks.
Great. Okay. So now that we have this data, how do we actually learn from this data? And this is actually a pretty tricky question. So if we look at the data, some of the data that I showed before, in contrast to settings where you're trying to learn a specific task, there's no notion of progress or success. And so we can't just optimize for high success, right? So it's not actually like immediately clear how we could use this data to learn lots of different kinds of tasks and learn things about the world. And so what we're going to do is we're going to, in some ways, take a very long-standing approach in robotics, which is to learn a model of the dynamics. Except what's different is that we're learning the model from the dynamics from this potentially self-supervised data, and we're learning this model directly in pixel space, directly in the space of the camera images taken by the robot. And we can get video predictions that look something like this, for example. We're predicting what the future images will look like as a function of the current image and the future actions that the robot takes. And in contrast to something like model-free learning, where you're trying to learn a specific skill, these models capture general purpose knowledge about the world. They use all of the available supervision signal, so they're being supervised by all of the pixels in the images. And further, by learning these models on top of images, there's also no assumptions about the representation that is given to the robot. And this means that you can apply it to things like deformable objects, for which there is no clear and obvious representation. Okay, and then the last nice thing about these predictive models is that it's inherently a supervised learning problem, where you're given what you should predict, which is the future images, as a function of the current image and the future actions. And this means that if you scale up large models, if you use large function approximators, this will lead to better predictions. For example, in this recent paper by Ruben Villegas et al., which was published at NeurIPS last year, they scaled up video prediction models to use very large TPUs, and they get predictions that look actually quite good. So the right is showing the ground truth, the left is showing the prediction from the model, and we see that it's able to predict the motion not just of the robot, but also of the pants or the towel with fairly high fidelity. Cool. And then once we learn how to predict, we can plan using the model. And the way that we can plan is we can use a sampling-based optimization using our model. So for example, if we have a certain image, we could consider a number of different action sequences, predict the future for each action sequence that we consider, and then execute the best plan. Optionally, you can also iteratively replan at each time step to kind of reconsider your previous execution plan based on what actually happened. This is essentially, this whole approach of kind of learning a predictive model and plan using that model essentially corresponds to MPC or model predictive control in image space or visual MPC. Okay, so this is the overall approach that we can use to learn from this kind of data. Even if that data doesn't have like a reward function associated with it, for example. And how this might work is you specify a goal, you then run planning with respect to that goal, and here's a prediction that you can get that is optimizing this goal of moving this pixel over here. And then once you come up with your plan, you can execute it on the robot and get the robot to move this pixel over here and kind of approximately fold the leg of this pant. And one of the things that's cool about this approach is that unlike the single task learning settings that I showed before, you can use a single model and plan to accomplish a number of different tasks. So using random data, you can accomplish tasks like lifting this, this stuffed animal and covering an object with a towel, and also picking up an apple and putting it onto a plate. And several of these are using held out objects that the robot hasn't seen before. The robot also hasn't been tasked with these sorts of tasks before. And using a mixture of random data and kinesthetic demonstrations, the robot can also learn how to do more complex tasks with a variety of different objects, such as sweeping objects into a dustpan, bringing a blue object closer to itself using a hook when it's constrained to this green region right here, and also using unseen objects like sponges as tools to wipe objects off of a plate. Okay, so now that we have a means to actually learn from this data to accomplish different tasks, this means that we can return to some of the questions that we were asking before. So for example, one of the questions that I asked at the beginning is, can we use data sets across labs and use that in a way that allows us to generalize better? And so what we're going to do is we're going to take that data set across labs, which we call the RoboNet data set. We're going to hold out one robot from that data set and then try to fine tune on a new robot that wasn't seen in that original data set. And it's worth mentioning that we're not only fine tuning to a new robot here, but we're also fine tuning to a new environment with new objects and a new camera viewpoint. So this is stress testing generalization to a significant degree and helping us understand whether this previous data set is helpful when we're trying to generalize to a new setting with a little bit of data. Okay, and then once we kind of fine tune our video prediction model on this new robot, we're going to evaluate that model on a set of tasks similar to the tasks that I showed previously. And what we did is when we held out the KUKA robot, for example, we compare training from a random initialization to training a model pre-trained on RoboNet. And we find that the model pre-trained on RoboNet is able to achieve a significantly higher success rate than a model trained with a random initialization and fine-tuned on 400 trajectories. And we also see that we're able to do better when pre-trained on RoboNet and fine-tuned on 400 trajectories than compared to training from scratch on 1800 trajectories. Now, this is only one robot. What happens if you look at other robots? If we hold out the Franca and fine-tune on the Franca, we see a similar trend where we see an improvement from random initialization compared to, we see an improvement from pre-training compared to a random initialization. And lastly, we see a similar trend on the Baxter. However, one thing that we found on the Baxter is that if we pre-train on RoboNet versus pre-training on the Sawyer, we actually do better if we pre-train on the Sawyer. And this suggests that actually adding data from the rest of RoboNet on top of the Sawyer data hurts performance compared to only pre-training on the Sawyer. And this suggests that we're underfitting when we're given all of the data from RoboNet. And so kind of overall, we see some signs of life and we see that sharing data can be quite useful when trying to generalize, but we have some growing pains. Essentially, when we try to scale these models to these much more diverse data sets, these models are actually struggling to try to capture everything that's in the RoboNet data set. And this is evidenced by this number right here, for example. Okay, and so what is exactly the bottleneck? I suggested that the bottleneck was underfitting before, but maybe we can dive into this a little bit more. In particular, we can take this previous paper that I mentioned from Ruben Villegas, which really scales models to be larger and leads to better predictions. And we'll use this to try to scale the model that we trained on the RoboNet dataset. And what we find is if we compare a model that has 75 million parameters to a video prediction model that has 500 million parameters, we see actually a pretty substantial gain when we increase the size of the model. So for example, in the smaller model, we see somewhat blurry predictions of the robot's gripper, whereas in contrast, in the larger model, the gripper is sharper. We also see that in the smaller model, there isn't any object prediction. It predicts that the object will disappear or that it won't move. Whereas in the larger model, we see that it is slightly better at predicting the object motion, but still seems to be underfitting to this data. And so even when we scale these models to have 500 million parameters, which is substantially larger than kind of the standard models that we use, we're still seeing underfitting. And we're still seeing that it isn't able to capture the motion of objects in the training data set. And what I didn't even mention is that this is actually just the Sawyer subset of the RoboNet data set. And so we'd actually expect to see even more underfitting if we trained it on all of the robot data in RoboNet. Okay, so this seems to be a pretty substantial problem when we scale to larger data sets. This problem of having models not being able to even fit even model things in the training data set. So this informs how we should develop algorithms that can learn from large data sets. And in particular, we're going to investigate two different paths for this. The first is building better models that can scale better to these large data sets. And the second is developing methods that don't require learning these predictive models. Maybe if we only learn a policy, we won't underfit quite as much. So I'll talk about these two paths. First, let's talk about better models. So this is kind of along the lines of trying to scale dynamics models to these large data sets. And the first thought we had here was, can we learn to only model what matters? There's lots of things in the scene that may not matter for different kinds of tasks. And maybe if we train the model to only care about the things that are relevant for different tasks, then it won't underfit. And so the first thing that we looked at here is, well, I guess one first approach or one kind of obvious approach here is to try to learn a representation using task supervision and then learning a model using that representation or on top of that representation. So for example, this might correspond to like standard state estimation approaches. It may also correspond to works that use a reward function to structure the latent space and learning a model inside that latent space. And while these approaches will work well if you can get a lot of supervision, they require significant supervision and significant engineering per task. And the representation that you learn for one task may not be useful for the representation that you might want for another task. So this doesn't seem like quite the right answer for scaling dynamics models. The second thought that we had is, well, maybe we can learn a representation that's tailored to a particular goal image. So we can represent a task as a goal image, and this is a way that we can represent different tasks without supervision. And then we could try to basically tailor the representation that we learn to that goal image so that it only models the objects that are relevant to solving that goal. And this is really nice in that it doesn't require any supervision, and it allows us to learn more tailored representations to these goals, and as a result, learn better models. And we found that it can successfully redistribute kind of where the model is being erroneous versus where it's being accurate based on the task. However, it's still kind of a direction that needs more research. We have this initial work at ICML this year on this direction, but it doesn't seem like quite the final answer on this line of research. Okay, so only modeling what matters seems like a good direction, but maybe somewhere, an area where we still need to think a bit harder about how to solve the problem. So the second direction that we've thought of is actually trying to scale the models themselves. And in particular, it seems like before the bottleneck was GPU memory. So maybe we could train models in a way that isn't bottlenecked by the memory of a GPU or a TPU. And the way that we can actually do this is we can look back at an old trend in deep learning where people were training neural networks layer by layer. This is something that was quite popular, actually. I think it was the de facto approach for training neural networks. It was introduced by a few different works. One of the original works was done by Jeff Hinton in 2006. And the way that it works is you train the first layer, for example, of an autoencoder by just training a neural network with one hidden layer to reconstruct the inputs. Then you can train the second layer to reconstruct these hidden activations, and so on and so forth. And one of the things you might notice is that this greedy training of a neural network reduces the memory costs, because you only need to train this network, you only need to train each module one at a time. And this network has much less memory cost than like a full deep neural network. So one of the things we can do is we can actually translate this to modern video prediction models, where we essentially first train a one-layer neural network to predict the sequence of future images as a function of the current image and the actions. And then once we train this, we can freeze this network and then train another network to predict the future variables as a function of the current variables and the action, and so on and so forth, to eventually train a kind of K-module video prediction model that is deeper and deeper with kind of as you add more and more modules. Cool, so the high level idea is that we can do this sort of greedy training, and this can save us on kind of GPU memory because each module doesn't require as much memory as the entire deep neural network. There's also a number of other details that go into the architecture, and I'll cover a couple of the high level bits. So first, we train the modules sequentially. We optimize each of these modules with respect to the evidence lower bound. So this is a latent variable style model trained using variational inference. And finally, one other important high-level bit is that the encoder of this model is compressing the spatial dimensions. And the reason why this is important is that the spatial dimensions of the activations of a convolutional network have significant correlations between different dimensions. And that's because images in general tend to have like very low frequency content. And when you're training things like variational autoencoders that use the mean field approximation, this mean field approximation assumes that each of your dimensions are independent. Essentially that like P of Z is equal to the product of like P of Z1 times P of Z2 and so forth. And if you have a lot of correlations between these different dimensions, then this mean field approximation won't be accurate. Okay, so those are some of the high level bits to these models. And now how well do these models actually work? So we asked a few different questions. First, how do these greedy hierarchical VAEs compare to state-of-the-art video prediction models, such as Villegas et al.? Second, do these models lead to better downstream planning? Also, how does greedy training compare to end-to-end training in settings where it's possible to end-to-end train these models? And lastly, can we actually start to overfit when training these video prediction models? And then we'll also look at a number of different metrics. In terms of measuring how accurate the dynamics model is, we'll look at FVD score, which looks at visual quality and temporal coherence, as well as this LPIPS metric, which looks at perceptual similarity to the ground truth. We need these two metrics because things like L2 distance and mean squared error are actually very poor metrics of the fidelity of a video prediction. We'll also look at human preference as well as success rate when planning. Okay, so let's first look at this first question. How do these kind of visual dynamics models compare to state-of-the-art video prediction models? And across 3 different data sets, the RoboNet dataset, the Kitty dataset, and the Human 3.6M dataset, we see a 20 to 50% improvement across the board in comparison to this model from Villegas et al., which is the largest model that will fit on a 24 gig GPU. So these are pretty substantial gains in performance. We also see a large gain in human preference of GHVAEs compared to this prior model by Ruben Villegas. So this is great. We have a better model of the world. Do these models lead to better downstream planning? To test downstream planning, we gave the robot a goal image. So in this case, the goal image is showing that the robot should basically kind of sweep this object into the dustpan using the sponge. And when we plan using our video prediction model, we see that the robot is able to kind of successfully accomplish that task by grasping the sponge and pushing the object towards the goal. And then in the second task, the goal is to wipe this kind of milk carton off of the plate using the sponge. And we see that the robot is also successful there. And quantitatively, when we evaluate this model on planning with 100% objects that weren't seen during training, we see a pretty substantial gain in the success rate from around 50% to 87.5 or 90% on these two classes of tasks. Great. And then lastly, two other questions that we were curious about were these last two questions. First, we found that when we actually took this architecture that we designed for greedy training, we found that greedy training actually works substantially better than end-to-end training. This is a result that actually surprised us quite a bit. And it suggests that greedy training actually leads to an easier optimization of these variational autoencoders. And second, we also found that if we look at train and test performance, these numbers are quite similar, which suggests that we're still underfitting to the RoboNet dataset. And it suggests that adding more modules, so this was a 6-module network, adding more modules may lead to better performance. Okay, so that's kind of one approach that we could take to handling underfitting, is building these better models, actually training neural networks in a greedy fashion rather than an end-to-end fashion. Dave, do you have a question?
Yeah, just is there like is that result like specific to RoboNet in some way, or should everyone just start training like variational autoencoders in a greedy way?
Yeah, so it is not specific to RoboNet. So the quantitative results that I showed, we showed results both on RoboNet, on Kitty, and on Human 3.6M. We haven't yet tried this for image generation. We've only tried it for video prediction. So it's possible that it is specific to video prediction. It may also be helpful for image generation as well. And it does seem quite promising to me that it may also work well for image generation.
Cool, thanks.
Okay, cool. So in terms of scalable approaches, I want to also just briefly end on how we might maybe use model-free approaches rather than model-based approaches. So maybe the underfitting problem is because we're trying to learn this like very large dynamics model to predict everything that will happen in the future. And maybe if we took a model-free approach, we would be able to overcome these challenges. And in this work, we're actually going to be looking at a problem setting that I mentioned at the very beginning, where we want to be able to learn from videos of humans doing tasks. So in particular, we want to be able to leverage videos of humans opening drawers, for example, in order to train a robot to open a drawer. And this is a setting where training a video prediction model on something like this would probably be quite challenging, because we'd need to model all these different kinds of drawers, the uncertainty about what will look like inside the drawer, as well as the human arm. Okay, so our goal is going to be able to leverage these videos as well as some robot interaction in order to solve the task. And the basic idea of how this is going to work is we're just going to add the videos of the humans to the replay buffer of the reinforcement learning agent and then run reinforcement learning. That's like the key idea. Now, you might be wondering, okay, well, how do we add videos to a replay buffer? These videos have domain shift. They don't have action labels, and they also don't have reward labels. So it seems like we can't quite directly add them. But it turns out if you basically take the simplest approach you could imagine for these three different things, then things basically just work. So for domain shift, we use adversarial domain confusion, which is a pretty typical approach for handling domain shift between two domains. We also used some images that were approximately paired from random robot interaction and the human videos to help it find a correspondence between the two domains. For the actions, what we did is we just learned an inverse model in the robot environment and used that to label the actions of the humans on top of the domain invariant representation. And then for the rewards, for the human videos, we just labeled the last state of the human video as having a high reward and everything else as having a small or 0 reward. Okay, so this is basically the entire approach. We just add the videos to the replay buffer and run reinforcement learning. And when we add them to the buffer, we do these three things to just add actions and add rewards to the replay buffer. Tanmay, do you have a question?
Yeah, I guess two quick questions here. One is that you mentioned you get paired images, roughly paired images from both the videos and the robot interaction, how do you get the pairing?
Yeah, I'll talk about that on the next slide.
Okay, and I guess the second question is, this assumes that there's like the robot interactions have some data that looks something like the human demonstrations, which seems like you have a pretty, like your robot's doing a reasonable job exploring to start with. Is that true, or is it just random interaction data?
Yeah, so we're actually going to be doing online RL on the robot side of things. So at the beginning of training, it's just going to be completely random. And then over time, it will be able to learn the task better and better.
Okay, cool, thanks.
Cool, so on the experiment side, we tried two different things. We tried this drawer opening task, and we also tried this pushing task, where the goal is to push the red object to the black target. And in the robots environment, it only gets sparse binary rewards. So 1 if it accomplished the task and 0 otherwise, and image observations. So this is quite a challenging reinforcement learning problem. And some examples of the paired data look like this. This paired data just used the initial robot policy, which was just random. So none of the paired data actually has the robot at the goal. And it's also fairly approximately paired. They're not exactly in correspondence, as you kind of might notice here. And the way that we got this paired data was fairly manually. So for this paired data, Carl, who is the first author in this work, basically just looked at the images and found images that correspond to each other. And then for this one, he actually just basically annotated where the position of the hand was, and also annotated where the position of the gripper was, which you could do with a color filter. And then just found images where the position of the hand and the robot gripper were in the same place. Okay. And then what we find is when we leverage these videos of humans, we're able to see a significant gain over standard reinforcement learning. So orange is showing reinforcement learning with videos, and green is showing standard reinforcement learning. This blue line is showing standard reinforcement learning with exploration bonuses based on R&D, which suggests that the human videos aren't just providing an exploration bonus, they're actually providing information about how to solve the task. And then further in simulation, in a setting where we don't have any domain shift between the videos and the robot, we also found that this approach improves substantially over imitation from observation methods such as BCO and ILPO, which suggests that we're actually benefiting from the fact that we have a sparse reward function and can use that to improve our policy. Okay, so that's kind of it in terms of how we might learn from different diverse data sources. So to summarize everything that I've talked about, the first is that if we want robots to generalize broadly, we should figure out how to train them with equally broad data. I think that as a robotics community, we need to think about how we might leverage broad data sets when training robots. This was first talking about how we should acquire that data, and we found that a small amount of guidance can go a long way towards getting good exploration data. And we also found that in terms of on the algorithm development side, underfitting is a really major challenge. But when we address these underfitting challenges, we can start to leverage diverse data sources and generalize more broadly. And all of these, I think, are in my mind, steps towards robots that can generalize more broadly and hopefully eventually go out in the real world. And then looking into the future, I'm really interested in how we might develop AI systems that more broadly understand the world that they live in. And in robot learning, I think that we've really only barely scratched the surface of data scalability. I talked about the RoboNet database and watching videos of people. And I think that if we can really figure out how to leverage these kinds of data sources effectively, we should be able to enable robots to generalize to lots of different objects and environments. And in AI more broadly, once we figure out how to scale to very large data sets, it seems like the next question is going to be, can we figure out how to generalize beyond the data distribution to allow models to be more robust? And this is also a direction that we've been looking at, trying to look at robustness to distribution shift and enabling robots to be robust to new environments, such as new backgrounds or transparent objects or different morphologies of the robot. So that's kind of a direction that I think is also important, although maybe not immediately important on the side of robotics, because we really need to figure out this data scalability challenge. Yeah, and with that, I'd like to thank my students, especially the students who were leading a lot of the work that I presented today: Annie, Suraj, Alex, Sudeep, who's actually at TMU, Frederick, Annie, Bohan, Carl, and Ole. If you're interested in learning more about some of these topics and about meta learning, which I actually didn't talk about too much today, I teach a course at Stanford and that has all the lecture videos available online. And I'd be happy to take more questions. Thank you, everyone.
Thank you. I thank our speaker. And now we have questions. So since we have a large audience today, so please raise your hand before you speak. And Chelsea, can you just ask people to ask questions?
Yeah, Xinyu, what's your question?
Hi, great talk. Since in the conclusion, you mentioned that underfitting is a big challenge. I wonder what are your thoughts on alternative ways of like learning this generalizable ability, such as injecting human knowledge, such as like notions of object and physics?
Yeah, so I think that injecting human knowledge could be an effective route for broader generalization, and it's kind of along the lines of some of the things that I mentioned at the beginning. It seems like that could be helpful. I think that I guess there's two ways to view it. One way to view it is it seems like those sorts of biases may allow things to generalize further, especially in settings where you don't have a lot of data. Although when you do have a lot of data, then I think that those sorts of biases that you inject into the system won't be quite as helpful, because the data will allow you to learn things about physics and about objects. And then the other thing is that in order to do that, we need to figure out how to inject that sort of knowledge into these systems. And it seems like so far we don't have great mechanisms for doing that, even if we do have like good notions of physics and objects, and that's like still an open research question.
Thank you.
Tanmay, do you have another question?
Yeah, thanks for the talk. So I like this idea of learning from general videos, and I think you'd probably agree that if we could get at that problem without having a poor grad student label correspondences between these videos, that would be great. Is that like, do you know how you'd like to approach this problem of learning correspondence without the grad student supervision, or is that something like you think we can do with unsupervised techniques, or is that something that we shouldn't be trying to get at all?
So I'm really excited about the prospect of learning from videos of humans, because it seems like there's so much data out there of humans doing really interesting things in many different environments and so forth. And that may make it more practical for us to allow robots to generalize. It seems like if we can figure out how to tap into that, I agree that finding a correspondence seems like a pretty core part of the problem. What I am maybe kind of cautiously optimistic about is that maybe we only need a little bit of paired data. And if we have some paired data, that will allow us to lock in the right correspondence. And the amount of paired data that we had in this work was like, I don't know, 500 images or something, which is probably a fair amount for just a single task. But if we only need that amount for lots of different tasks, then I think that would be great. And that would be at least a solution that I'm very happy with. It may also be possible to do it in an unsupervised way, but I think it's going to depend a lot on the data distribution itself. If a lot of our robot data is random and a lot of our human data is really sophisticated, then it may not be practical to find a correspondence in a completely unsupervised way, because there's both the domain shift and also the difference in the behaviors that they're executing.
Yeah, thanks.
Arpit?
Thanks for the talk. I was thinking about that, like in most of your work, the starting point was that we have an image and we try to use that for both the representations and the goals, definitions or targets. So I was wondering, what is your opinion regarding like using other forms of representation? For example, like like point clouds or in places like surfaces to either do reasoning or to do sort of define those sort of goals. And like one other quick question was regarding like in all the data sets, do you think defining a task also might be useful for sort of like when we are sort of designing these data sets?
Yeah, so for your first question, I think that task specification is a really important and challenging problem, and kind of actually probably one of the biggest missing pieces that I didn't really talk about today. And we kind of worked around by providing like an image of a goal. I'm not exactly sure what the right solution is there, whether it's point clouds or images or language or something else. It does seem like there's a bit of a trade-off between what makes it easy for humans to specify tasks. Things like language would probably be one of the easier ways to do that, versus what the robot can interpret. Of course, having the robot ground language is like a whole nother research problem in and of itself. And if we're relying on grounded language learning to specify tasks, then it seems like that might make it harder to make progress. But yeah, overall, I think that's a really important problem, and we should think critically about that. What was your second question again?
So in terms of the design of the data sets, either like to scale them, I think one of the biggest challenges which I see in terms of using or sharing the data set is the definition of the task. Like whenever somebody wants to use the data set, they define their own task because they want to solve or sort of highlight a different aspect of the problem that limits the usage of the previous data set or like benchmarks.
Yeah, absolutely. So I think that having some sort of annotations on these data sets would be really, really helpful. To say like, oh, the robot accomplished this task or it accomplished this task in this video or at this frame. And I think that that would be really helpful especially for like applying model-free like methods as well. And for learning this sort of task specification, language annotations could also be super helpful. And also having kind of a common set of tasks that we evaluate on to make things comparable. Ideally, it wouldn't just be one task, because I think that generalization across tasks is important. And one of the big benefits of using these data sets is that it does allow you to generalize across tasks. But exactly how we do that is also kind of a challenge.
Thank you.
Tanmay, do you have another question?
Oh, sorry, no, my hand's still raised. My bad.
Mernal?
Hi, Professor. Thanks so much for the talk. You talked a little bit earlier about challenges with finding other representations of the environment, like using kind of other methods for tracking objects and poses and whatnot. Can you expand a little bit more? Because at least to me intuitively, that seems like a cool way to, or it might be easier to learn representations of the environment if you're not stuck with a specific kind of viewpoint and images.
Yeah, so you mean basically the learning a representation and learning a model inside that representation?
Yes.
Yeah. So it seems like there's kind of these two things. One is we could use supervision, which doesn't seem quite appealing because it seems like that might be task specific and also requires a lot of supervision. And then this approach is kind of, we're looking at trying to have a representation that's tailored for a goal image. And the way this works, it kind of works in two ways. First, the representation is conditioned not just on the current state, but also on the goal image. So this allows it to learn a representation that is kind of specific to the goal image. And second, the way that we learn this representation is we decode it into this residual between the predicted state and the goal state.
Mm-hmm.
And if any distractors in the image are stationary, then this will discard any information about task irrelevant distractors and only pay attention to things that are different between the current image and the goal image.
Okay.
That said, these sorts of residuals, if you have dynamic objects in the background that are distractors, like a human walking by, then these images will also capture those distractors. So it's not kind of the golden solution for everything, because it's hard to disentangle things that matter for the task, like objects, and things that are moving in the background, like people. And there could also be a task where you want the human to go into a certain location, and it's kind of an underdefined problem. It's not clear what matters and what doesn't matter. There's also another approach in this paper where we try to upweight trajectories that do better on the goal, because those are things that are inherently interacting with things that are relevant for the goal, and downweight trajectories that do other things that aren't relevant to the goal. And there's also some nice theory in the paper that suggests why something like that might be a good idea. But that unfortunately didn't work quite as well. And I think we need a bit more research on that to figure out what a good approach would be.
Okay, thank you. I'll go check out the paper.
Okay, thanks everyone. It's already time. So let's say it's the official end of the RI seminar today. But traditionally, we do have a post-seminar session for people to talk around. So Chelsea is very kind to offer to stay here for a few minutes longer so that we for